Hello. Super. Bitte multiparty computation.
Good morning, everyone. Wow. Now you're awake, I'm sure. Welcome to the session on threshold cryptography. My name is Dominique. I'm happy to chair this session. We will start with the first one, Threshold Crypto 1, which is also known as the Aarhus session. So the first talk is Secure Multiparty Computation from Threshold Encryption based on class groups by Leonard Brown, Ivan Damgard, and Claudio Orlandi from Aarhus. So many thanks for being here, and let's get started.
Thanks for the intro. Yeah, I'm Leonard. I'm giving the talk, joint work with Ivan and Claudio. So first, I'd like to go through the title, the 3 parts, and then give some other supplementary intros. So this is the first talk of the day. So let's start with MPC. Well, we have a bunch of parties. Every party has some input. And now the parties would like to compute a function based on their private inputs without revealing anything else. Now, ideally, we had some magic box. Every party could send their inputs to this magic box, and they would receive the output. So this is obviously as secure as it gets. Every party sees only their inputs and outputs. Now, we cannot assume we have such a magic thing, so the parties need to run a cryptography protocol. So in the end, they get the output, but without learning anything else. And this is basically MPC. Second part, threshold encryption. Kind of the same setting. We can see it as a special case. We again have a bunch of parties. They run a protocol, and out comes a public key. And additionally, every party gets a share of the secret key. But nobody sees the secret key in plain. Now that we have the setup, we can take a ciphertext. And as long as there are enough parties around and are willing to participate, they can run a decryption protocol, and out comes a message, again, without seeing the secret key. So for the third part, class groups, well, I don't want to talk about class groups, but instead I want to highlight the work of Guillaume Castañas and Fabien Laguémie, who gave us a nice framework, a nice abstraction to work with these class groups as groups of unknown order without having to deal with the mathematics behind them. So they give us a parameter generation algorithm. We input the security parameter and a large prime of our choice. So anything larger than 2 to the security parameter. And out comes a class group, and this class group has a subgroup G, which factors in G to the Q and F. Now F is a subgroup, or the unique subgroup of order Q, the prime we have chosen. And then this subgroup, the discrete logarithm is easy to compute. And the second subgroup is G to the Q, the Q's powers. And in contrast to F, here we do not know the group order. And in fact, it's a hard problem to compute the group order or the order of any element in this group, or even a multiple of that, which is the unknown order assumption. And as an additional hardness assumption, we have the hidden subgroup membership problem, which basically says it's hard to distinguish random elements in G and in G to the R. So we can say this kind of hides this F component. Why are we interested in this? Well, first, we can choose Q freely. If we have already a big prime in our protocol and we need to do something over the same prime field, we can choose the same prime here. So that's very nice if we want to use this tool in higher level protocols. Then we get transparent setup. This class group has no trapdoor. In RSA, for example, if you know the factorization, you can compute the group order, but here there's no such thing. So we get like a public coin setup. And finally, we get an encryption scheme that is linearly homomorphic, but faster than Payet and even has smaller ciphertext. So the encryption scheme looks as follows. The setup is again parameter generation with a prime that defines our message space. We can choose it freely. Key generation, as in any DLOG-based encryption scheme, we sample some big random secret key, and the public key is just G to the secret key. Now, encryption looks very similar to El-Gamal, where the message in the exponent, we sample some randomness, have G to the randomness, and then hide the message with public key to the R. But here we have the message in the exponent of F. So that means, first of all, it's linearly homomorphic. If we multiply ciphertext, we sum up the messages. And since the DLOG is easy, we are not restricted to small messages, as in the case of lifted El-Gamal, but we can decrypt any ciphertext of this form. So overall, this is secure because of this hidden subgroup membership assumption. And we can see this as an analog of the Kamini-Shoup encryption for class groups, whereas Kamini-Shoup works in the same setting as a Payet. So we took the encryption scheme and built a threshold version out of it because we want to do MPC. And for MPC, there is this old recipe by Kramer, Damgaard, Nielsen that says if you have a threshold linearly homomorphic encryption scheme and a bunch of zero knowledge proofs to prove things like, oh, I know this plaintext that I have encrypted here, or I have done this homomorphic operations correctly, then you get an MPC protocol. And the blueprint is quite simple. For every input, we just encrypt it and prove that it's done correctly and that we know what we have input. So linear operations we can do locally on the ciphertext, no interaction needed. And for outputs, we have the threshold decryption operation. Now, multiplications are always a bit more complicated. So given that we have ciphertext containing the two inputs of the multiplications, x and y, we want to compute a ciphertext containing their product z. So first, we sample a random mask d, and once as an additive secret sharing, and then also as a ciphertext. And that we can use to transform one of the inputs in an additive secret sharing. Here it's x. Now, everybody has as an additive secret share of x. They can multiply it with the ciphertext containing the other input y, and then broadcast the resulting ciphertext together with the proof that this was done correctly. And every party can add up the resulting ciphertext to get like CT of z. So that's the high-level overview of the MPC scheme, and that's all I want to say about it because, well, it's relatively simple once you have the building blocks. A few words more about our setting. We want to have active security. We have an honest majority setting with static corruptions, and we assume to have a broadcast channel. So honest majority was actually more interesting to look at it compared to dishonest majority because we can achieve guaranteed output delivery, and yeah, that makes things more exciting. Moreover, we want to have this transparent setup, which we get by using the class groups. So far for the intro. Now I'd like to highlight a bunch of tricky parts that came up in the course of the project. And first of this is part of the zero knowledge proofs. So as a simple example, this is nothing new. Let's just look at Schnorr's protocol, but over the integers. Why over the integers? Well, we don't know the group order, so we can't work modulo the group order. We have to do it over the integers. So we have the standard DLOG relation. We do everything normally. We sample some random R, send over G to the R, get back a challenge, and answer this challenge as a normal Schnorr's protocol. However, here we compute it over the integers. We don't have this modular reduction, and therefore we need to sample R large enough so that we get honest verifier zero knowledge, and that it hides the witness. Otherwise, it's more or less the same. So what about soundness? Well, normally we have two special soundness, giving two transcripts that are both accepting with the same first message, but different challenges. We can extract a witness by just computing u minus u prime and dividing out k minus k prime. Of course, modulo the group order, but well, we don't know the group order, so division is kind of tricky. And does it work over the integers? Well, if the prover is honest, then yes, but we cannot rely on this. So say there's some prover coming up with convincing proofs, and the division might not work over the integers. What could we do? So one solution is binary challenges. Division by 1 and -1 is kind of trivial. So that's good, but we have to repeat the protocol to get proper sounds. Other option, rely on some computationally hard problems and prove that either this division works over the integers, or we can solve some hard problems with a prover that prevents us from doing so. But the strong root and low order assumptions that have been used in the past made things a bit more complicated and also required some additional setup, which we would like to avoid. Now, in our setting, we observed that for most of our cases, set membership soundness, so just existence of a witness, is actually enough. And we don't necessarily need to extract the witness. So compared to prime orders, the statement might seem trivial, because in a prime order group, you can often see, oh yes, H is indeed a member of the group generated by D. So why is your knowledge proof? Well, in this class group setting, it's a bit more tricky. You often cannot determine if the group element is in the right subgroup. So we need to prove it to make sure that the overall protocol goes through. So our solution here is we came up with a new assumption, which we call the C rough order assumption. C is a natural number, say 2 to the 128, and we assume the following distributions are indistinguishable. Class groups that came out of this parameter generation algorithms, and those class groups that have a rough order, meaning there's no small prime factor in the order. Now, but before we think about is this realistic, let's see how it helps us. So say we have a C rough order, then it means every number between 1 and C is co-prime to the order and therefore invertible. Therefore, K minus K prime inverse exists and the witness must exist. So we get sound proofs. Now, why is this justified? So there's this Cohen-Lenz heuristic, which very roughly says class group orders somewhat behave like random integers. And therefore, there must be significantly many class groups with a rough order. And moreover, had we an efficient distinguisher, then we could just use this distinguisher to generate class groups until we find one with a rough order. So we were fine with that, and it helped quite a bit in making our protocols more simple. Next part, how to build threshold encryption. Well, ideally, we would realize the following functionality. First method is key generation. The functionality just samples key pair, stores safely away the private key, and outputs the public key. And then if there are at least T+1 parties that come and want to have a ciphertext decrypted, the functionality uses a stored key and decrypts the message, sends them out to the party. So we have to somehow store the secret key, and at least T+1 parties needs to do something with it. So we need to have some TN secret sharing. And moreover, we need to use the secret key in the exponent of the ciphertext element, which is an unknown group order element. So we need to have reconstruction in the exponent, but we don't want to do it in the plane because we don't want to leak it, of course. So the standard blueprint is Pedersen's protocol for key generation in the discrete log setting. Every party samples a big contribution alpha I, and then publishes G to the alpha I, and also secret shares it. And then we can define the public key and the secret key as the product and sum, respectively, of these contributions. Now, there are a few steps missing, which we will fill out later, but this is already like a semi-honest protocol. Now, what about secret sharing? Well, we don't have a field element, we have a big integer, so we need to do integer secret sharing. And following the approach of threshold RSA protocols from the 90s, we use secret sharing over the integers. So we take a random polynomial with big coefficients, put the secret in the constant term, and then give every party a point on this polynomial, and these big coefficients should hide the secret. Well, the first issue is we don't have the modular reduction, so the point fj, f of j modulo j already leaks a secret modulo j. So we need to prevent this leakage. And the solution to this issue is that people have defined a public constant, year delta, as number of parties factorial. and just multiplied the secret by delta before sharing it, which prevents this leakage. So everybody just sees 0 instead of a part of the secret. So far for sharing. What about reconstruction? Standard argument Lagrange interpolation gives you back the polynomial, also works for integer polynomials, but here the Lagrange coefficients are rational numbers, not necessarily integers. And if we want to do this in the exponent, we have this division, so it doesn't work directly. However, solution multiply by delta and the denominators go away, but we reconstruct the secret times delta squared. So now we have a secret sharing scheme, and we can plug it into Pedersen's blueprint for key generation, but we want to have active security. So we need to make sure that all the stuff that party I does here is consistent with each other. So next step, verifiable secret sharing. There's Feldman's protocol, which is an extension of Chamier secret sharing. And in addition to the polynomial and the shares, we also broadcast some commitments to the coefficients of that polynomial. And we also need to prove that these commitments are in the right group. So one example as an application for the zero knowledge proof for D-logs that I mentioned before. Now, these commitments allow every receiving party to evaluate the polynomial in the exponent and make sure that their point lies in this polynomial. And assuming the unknown order assumption and that this data constant is co-prime with the order, and that we have a proof of knowledge for C0, we get an integer verifiable secret sharing scheme. So if at least T+1 parties are happy according to this check, then their shares will define an integer value that can be reconstructed. And while trying to prove this, we found like a minor issue in an old, very similar protocol by Tarabin for the case of threshold RSA. And there, the order assumption was not used. So in principle, an adversary that would know the order could prevent reconstruction of this secret. However, this is not a problem in the case of threshold RSA, or in our case, because reconstruction happens in the exponent, but it would not be a standard integer verifiable secret sharing. Okay, so we have a way to prove consistency. Now, what if somebody doesn't play according to the rules and something goes wrong, parties complained, and there's a complaint resolution phase. So in the end, we have a set of remaining parties that everybody agrees upon these behaved according to the protocol. So we adjust the public key and secret key accordingly to the parties that are left. But that also means by misbehaving, you can influence the distribution of the public key. And Gennaro et al. observed exactly this. A rushing adversary can make parties drop out to influence this distribution. They gave a way to fix this by using a more complicated protocol with more rounds and extra setup to guarantee a uniform, or in our case, almost uniform public key. But they also showed that it was fine for Schnorr signatures. So the question, of course, can we keep the simple protocol? Is it also fine in our case? And the answer is yes. And similar results have been shown for Elgamal in the past. So we allow the adversary to bias the distribution. We normally sample a key pair, give the public key to the adversary, and then the adversary specifies some bias that we use to adjust the key pair. Now we can prove NCPA security just by taking a ciphertext under the normal unbiased public key, use this delta, and create a ciphertext under the biased key. And then, well, this reduction goes through. So it allows us to keep this simple one round once we make the proofs non-interactive. So the simple protocol, and we don't have to deal with the extra setup for the Pedersen VSS. So having the one round key generation is especially useful for a setting called YOSO. So YOSO is short for you only speak once. It's a recently popular paradigm for large-scale MPC with lots and lots of parties. The work, however, is done by lots of small committees. And well, the special case is that every committee only has one round of communication. And the idea behind this is that an adaptive adversary can only figure out who is on these committees after they have spoken, but then it's useless to corrupt them because their work is done. And here we have some mechanism to send secret data to future committee members before they are known. Now, why is our work useful in this case? So first, using this CDN paradigm, the secret state is quite small. We only have to pass on the secret key, that is secret shared, towards the next committee. All the intermediate values are given in public ciphertext, so they can just be public somewhere on the internet. Then, well, we have this one-round key generation and decryption protocols, so we can do exactly this in a YOSO setting. And this also solves the problem of transparent setup for the encryption scheme in YOSO. So to summarize, we have the first actively secure threshold version of this HSMCL encryption scheme. We have UC secure multi-party computation using the CDN paradigm, where we can choose this prime field that we work on freely. We have a bunch of new zero knowledge proofs, and we adapted everything to the YOSO setting, so to make YOSO computation work. What's next? Well, Castaños, Lagumi, and Taka also came up with a threshold version of a different variant of this encryption scheme, where the plaintext space is the integers modulo a power of 2. And yeah, one obvious question is, can we adapt our techniques so that we get also MPC and YOSO MPC, etc. in the setting? Because, well, Z2K is very nice because it's represent what we have in our CPUs very well. And otherwise, we have this very nice and threshold-friendly encryption scheme. Can we build a CCA secure variant in like Kramer-Schub style, for example? The full paper is in ePrint, and well, thanks a lot.
Many thanks for the nice talk. You have now a few bit time of questions. So who wants to go first? No, you should not leave. You should ask. Okay, so let me ask one quick question. So you mentioned at the very beginning that you essentially achieve security against static adversaries. So what about active, well, basically adaptive security?
So we have not tried to prove it, but we used some techniques from other papers of key generation, namely like a, what was it called? So you kind of, in many adaptive proofs, you assume that one party is not being corrupted. And if that's the case, everything is fine. So we kind of use this technique in our proof, but in this case, we know that this party is not corrupted. So I guess we could just extend this corresponding to what the other people did before. But it was not a focus.
Okay. Are there more questions? Yes, please.
Thanks for the talk. Have you worked out concrete parameters or implemented the scheme?
So we have not implemented the scheme. There was this bicycle library that was on the slides by Bouvier et al. So they implemented the encryption scheme without the thresholds part. And they showed that it was like smaller and faster than Payet with this. So I think a group element for 128-bit security was something like 1,300 bits. Yeah.
And then now what's, when you say group element, that's like a ciphertext essentially.
That's half a ciphertext.
Half a ciphertext. And what would the clear text space be?
That would be, for example, 2 to the 128, like a prime of that size.
Okay, thank you.
So for the people that are online, you can also post questions in the chat. If there are no questions, then let's please thank the speaker again. And we're now getting ready for the second talk in this session. correct version of the slides? No, it's too late. So the next talk is two-round stateless deterministic two-party Schnorr signatures from pseudorandom correlation functions by Yash Kondi, Claudio Landi, and Lawrence Roy. And Yash will give the talk.
Fine now? Okay, so the motivation for this talk is the setting that cryptographic keys are generally pretty valuable targets, in that in this case, for instance, Bob has a bunch of Bitcoin that's tied to some secret key that he stores on his laptop. And storing a key on a single device is a bad idea because it can be a single point of failure. In particular, an attacker can turn up, steal Bob's key and any funds that are associated with it. And this is a bad situation. So threshold signatures give one kind of solution to this sort of problem, which is to allow Bob to split his key into two halves, so that every time he wants a signature, these devices have to run some sort of protocol in order to produce a signature. Yeah, so the idea behind distributing signing is to sort of distribute the risk of compromise. In this particular talk, we're going to look at de-randomizing two-party Schnorr signing in such a way that it's resilient to state resets. I'll get into what all of this is during the talk, but basically the conceptual insight over here in this work is that just like pseudorandom functions can de-randomize single-party signing, we showed that there's a native way to de-randomize two-party signing or multi-party signing using pseudorandom correlation functions. We give a couple of constructions to instantiate this framework that makes some nice trade-offs relative to previous work. And it's in the title that we get two-round signing, and I don't really explore this in the talk so much, but yeah. So as a quick recap, Schnorr signing begins by sampling a secret key SK from ZQ and exposing it in the exponent in the form of the public key. So that's a key generation, and then signing involves first sampling a nonce K, exposing it in the exponent as capital R, and then signing itself is sort of a linear combination of these two secrets, the signing key and the one-time nonce. And verification is straightforward. You just check the equation in the exponent. And it turns out that because Schnorr's scheme makes only linear use of all of its secret values, there are fairly straightforward ways to distribute its signing. So if you use any linear secret sharing scheme, it's pretty easy to construct protocols to distribute Schnorr signing. Schnorr signing is pretty well motivated, and distributing it is pretty well motivated because it's widely deployed in many forms, DSA being one of them. This is a variant that was devised by Bernstein et al. And it's a variant of Schnorr's scheme that's carefully instantiated. And yeah, let's take a look at DSA. And it's pretty much Schnorr, but it differs from Schnorr in this one small way, which is that the second half of DSA is pretty much the same as Schnorr. The equation is the same. But the way it samples its nonces is different. Where Schnorr samples a random nonce from ZQ, DSA evaluates the PRF. And as we know, distributing PRFs is kind of painful. So if you want to construct a multi-party protocol for DSA, we have to maybe think about why this happens, like why there is this weird nonlinear way of deriving nonces. The short version, the short explanation is that notice that Schnorr involves sampling nonces every time you want to sign. And it turns out that the distribution that these nonces come from is extremely important. It has to be uniformly random. There are all kinds of attacks that kick in if there's even a bit of bias. And this is a concern in practice because true randomness is not that easy to come by online on the fly. There have been many attacks that have reduced the fact that bad randomness is being used online. One way that you could think of de-randomizing any signature scheme or any distributed signature scheme is just by maintaining some sort of stateful pseudorandom number generator. So you keep some sort of counter, and every time you hit a button, you get the counter increments, and then you get a fresh random value. Unfortunately, it turns out, I mean, it's easy to see that if you repeat state, if you reuse a counter in this mode of operation, you will reuse a nonce, and that's a catastrophic failure that you'd like to avoid. And it turns out that this notion of state continuity in a lot of cases is quite non-trivial to avoid, even if you have powerful tools like trusted hardware. So there are many situations where you could end up reusing state. Think of if you were to load a stale VM snapshot, or there's some sort of power supply interruption and you reset to an old state and so forth. So basically, stateless signing is well motivated in a lot of situations. Yeah, so there's a simple way to statelessly de-randomize signing for Schnorr in the single party case, which is to use a PRF. That is, you sample a PRF seed offline, and every time you want to sign a message, apply a PRF on the message that you want to sign. This is the classic idea, and this is the one that's used by DSA and is the source of its nonlinearity and so forth. I do want to point out that this change is basically undetectable outside the system. So nobody outside the system knows that this method of de-randomization is happening. So you could use randomized Schnorr signing in the single party or multi-party case and still be fine. But it's still well motivated to think about how we could statelessly de-randomize both single party and multi-party signing for the same reasons that DSA uses de-randomized signing. Okay, so this is a simplified version of Schnorr's two-party protocol. I'm going to highlight the part that's important, which is just the first step. Just like in single-party Schnorr signing, sampling a nonce is the only randomized step. In the two-party case, sampling a nonce interactively is the only randomized step. Intuitively, it's just that both the devices pick fresh nonces by themselves, and these nonces sort of work as additive shares of the joint combined nonce. So let's think of a simple way that we could de-randomize this two-party protocol. Both of the devices could pick their own PRF keys during key generation. And when the time comes to sign, they do the same thing as DSA, which is that they apply a PRF on the message that they want to sign to derive their nonces. And then they exchange their nonces and continue with the protocol. It turns out that this simple mode of de-randomization has this unfortunate attack, which functions like this. Imagine if you were to sign the same message twice, right? The honest party, being honest, follows the protocol, applies its PRF and so on, and ends up deriving the same nonce share that it did the first time it signed the message. But there's nothing that binds the attacker to using the same nonce the second time. There's nothing that binds the attacker to actually applying this PRF to derive its nonce key. I'll spare you the details, but what ends up happening when there's a lack of verifiability over here is that if you work through the equations, what happens is that the attacker is able to collect two different linear combinations of the honest party secrets, because the honest party uses the same secrets in both instances. And the secret key just kind of drops out. This is the first observed by Maxwell et al. So now let's think about how we can fix this problem. Right? The problem is fundamentally that we weren't verifying that the PRF was correctly applied. So we could think of maybe including some sort of commitments to the seeds that both parties use. And online, when both the parties exchange their nonces, we ask them to include zero-knowledge proofs that say that they're deriving their nonces correctly with respect to the seeds that they'd committed earlier. So this sort of removes any wiggle room that both parties had in lying about their nonce or whatever. And this is sort of a GMW type approach. You just commit your randomness once and then prove in zero-knowledge that you're following the protocol with respect to your committed randomness. And this is indeed the approach that's taken by pretty much the only prior works that I'm aware of in this setting. And there is a lot of room in figuring out how to instantiate these zero-knowledge proofs, because the statement that you have to prove in zero-knowledge is pretty non-trivial. You have to evaluate a PRF and then prove that you're doing the exponentiation correctly. And there's different approaches to this problem, basically as much diversity as there is in instantiating zero-knowledge proofs. But whatever trade-offs you decide to make in instantiating the zero-knowledge proof, you're always going to be bound by this fact that when you're proving things about a PRF, when you're non-black box in a PRF, you will inherently be bottlenecked by the circuit complexity of the PRF. And this is something that you would ideally like to avoid, because PRFs tend to have not that convenient circuits. So the main question that we ask in this paper is how we can statelessly de-randomize Schnorr signing in such a way that we can make black box use of cryptography, that we don't have to depend on circuit complexities of PRFs and so on. And the answer that we give as to whether this is possible is a very qualified yes. And so it's not like it's not the end of this line of research. It's sort of just a beginning of towards a great answer for this. Our main construction is sort of this meta protocol that makes use of these pseudorandom correlation functions, or PCFs, for the vector oblivious linear evaluation correlation in ZQ, where Q is the order of the elliptic curve. And this, I claim, gives a pretty simple native stateless de-randomization pattern. And PCFs are a sort of increasingly general cryptographic object. They're pretty new, but it's not, while we're generic in PCFs, PCFs are not OT, right? It's reasonable to say that you're using generic assumptions if you have something as fundamental as OT, and PCFs are not exactly that. We do give a couple of concrete instantiations for these PCFs, one that achieves covert security generically from any pseudorandom function, and another one that makes use of a specific technique using pi. Okay, so as a quick reminder, a pseudorandom correlation function, or PCF, was introduced by Boyle et al. In this work. And roughly the way it operates is that there's a one-time setup phase in which some correlated seeds are distributed to a couple of parties, to the two devices that are involved in the system. And after this one-time setup, an unbounded number of times for any public instance X, each of these parties can locally evaluate their PCF functions with these correlated seeds to derive some outputs that by magic will be correlated as per some a priori correlation Y. So you can define arbitrarily complex correlations for these outputs to satisfy. But of course, we want to be careful when we do this because the complexity of the correlation will determine how efficient or otherwise any PCF function to realize this correlation will be. So the game here is finding a good enough correlation for Schnorr, something that is simple enough for so that it permits reasonably efficient PCFs, but at the same time, it's powerful enough to build something non-trivial. And I claim, or rather what we find in this work is that the Wole correlation has a nice trade-off in this sense. Very roughly, I've adapted the Wole notation to kind of match what we use in this paper, but basically one party on evaluating the PCF gets its private nonce and also a MAC on its nonce in such a way that the keys for this MAC are held by the other party. This MAC here is basically just an information theoretic thing. It's a pretty standard format for a MAC. It's a simple linear combination. And the way that you can use this correlation is that the party that gets the private nonce claims its public value R to the verifier. And it also has this MAC W that authenticates its private nonce. And it can just send W in the exponent to the verifying party. And the verifying party has its MAC keys, which it can just check in the exponent to make sure that this first party, the prover party, is not lying about the nonce that it got out of this correlation. And the intuitive idea here, just as most macking schemes work, is going to be that the prover party has to effectively guess this delta, this MAC key, in order to subvert this check. So if the prover wanted to claim some different R from what it actually got from this correlation, it has to kind of guess what the delta is on the other side. The first construction that we give to instantiate this uses this nice technique of Roy that is built from OT, that was introduced in the context of OT extension. Essentially, the seeds of the PCF correspond to a bunch of PRF keys, of which the prover gets all the keys and the verifier gets all but one. And the idea is that these PRF keys are going to be evaluated on any public input and combined in some clever way, so that as long as the prover doesn't know which key the verifier is missing, the prover won't be able to subvert the check. The details are not super important here. But because the MAC key in this case is the verifier's index, it just indexes which key the verifier doesn't know. This is a small set. The index is pretty small, so the prover can, in theory, guess which key the verifier is missing, and it's only polynomially sound, which is kind of annoying because let's say the highest reasonable security you can achieve is like 2 to the minus 10 or something, but it is still statistical and maybe meaningful in some cases. It's unclear, unfortunately, how to extend this to a fully malicious secure construction. And so we have to look to other techniques for a full malicious secure thing. Orlandi, Scholl, and Yakubov came up with this really nice construction for Wole PCF based on Pi a couple of years ago, which does support exponentially large MAC keys, so like exponentially large Wole correlations. Unfortunately, the correlation that they provide is in a ring Zn, where n is an RSA modulus effectively, and it's of unknown factorization. But what we want is a correlation mod Q, where Q is the elliptic curve group order. So we have to come up with some gadgets that let us translate this correlation mod N to a correlation mod Q. And this turns out to be kind of non-trivial. We had to borrow some ideas from previous work in this regime. So very roughly, both parties start out with this correlation mod N, and what they want to achieve is the same correlation mod Q, like a similar correlation mod Q. The details aren't super important. This is just to sort of give a flavor of the techniques. But the idea is that the prover, the one with the secret nonce, splits its nonce into a residue and a quotient for some public modulus M. So K high is the quotient, K low is the residue, and K low is going to be the private nonce at the end. The private nonce that satisfies the correlation mod Q. And if you're familiar with IKNP, OT extension style stuff, the prover basically sends a correction word over to the verifier, K high, so that the verifier can use K high to do a simple linear adjustment of its MAC keys in order to translate its MAC from mod N to mod Q, something that works mod Q. It's basically like adjusting your input in an OLE, if it's a pretty simple operation. So yeah, the problem is, what if the prover sends a bad correction word, something that's malformed? Right? What happens to for any k high value, what happens to the k low value that it induces? Right? The tricky thing is that deriving a correct correlation isn't enough. What we want really is something that's resettably sound. That every time the prover sends a k high value, like the prover runs this protocol many times with the same correlation and sends different k high values, the k low value that it induces in the final correlation has to be the same, because we don't want the prover to change things just by resetting the verifier. Yeah, there's a lot of nuance to this, but intuitively, as long as we can make sure that the final correlation that the verifier translates to holds over the integers and not just mod n, like there's no wraparound in the final correlation, we're fine, we're good to go. That's just the high level intuition, and the way that we can do that is by making sure that this residue value that's implied by k high is small, right, for some notion of small. And the way that we can do this is, I mean, it's kind of easy to fall into these traps of range proofs and so on when you're working with groups of unknown order. We introduce an auxiliary RSA modulus n tilde, and we have a check that's modulo this auxiliary value. Basically, the same correlation is checked in this other group of unknown order to make sure that the prover isn't cheating. Yeah, and we prove that this check is sound, assuming the strong RSA assumption. If you're familiar with the Damgov-Fujisaki integer commitment scheme, the techniques are kind of similar to that. As for efficiency, a quick note about that. The covert construction is basically the same as semi-honest, or like it's fairly close to semi-honest signing, so it's almost a free upgrade. The malicious construction that I just showed, that's based on pi for standard parameters. Here's a quick comparison to previous work. I don't want to get too hung up on the details because it's not a very like mature area, but effectively it takes about half a kilobyte to send the correlation correction word along with the check, which is about half as much as the next best thing, which is using bulletproofs or some kind of snark thing, which is much less in bandwidth than the garbage circuit approach, which is also taken by previous work. It costs just under a couple of 100 milliseconds to generate all of these values, which is maybe an order of magnitude worse than creating a garbage circuit that would serve the same purpose, or using a snark like bulletproof that also serves the same purpose. So that's sort of, there are trade-offs to be made here is the point that I want to make. So far I've been talking about all these protocols in some sort of ideal setup model. And yeah, it's important to think about how to distribute this setup as well. It's pretty straightforward for the covert construction, but for the malicious construction, on the face of it, it seems like you need to sample an RSA modulus inside of MPC, but it's not actually that bad because it turns out that each party can know one of the factorizations. The prover can know the factorization of n, and the verifier can know the factorization of n tilde. In principle, these two parties could just pick n and n tilde themselves locally and prove in zero knowledge that they're well-formed. But we focus on signing in this work, so we don't really explore exactly what the prover has to choose, what each of these parties has to say about their moduli to prove that they're well-formed. Right, so in conclusion, we give a protocol that's based on PCF that seems to be a natural fit for statelessly de-randomizing two-party Schnorr signing. We give a couple of instantiations for the PCF that we use, that one of which is based on generic assumptions using the soft-spoken OT technique, and the other one that's based on this pi-based wall, and with some new gadgets for this to make everything go through. Thanks.
Many thanks for the nice talk. We have some time for questions.
Thank you for the presentation. Have you explored how to do secret resharing and keeping the property that the signatures will remain deterministic? Meaning after resharing, if you sign the same message, you still get the same value?
Oh, that's a good question. So if you get, so let's say you have some epoch, reshare the secrets, and then you run the protocol again. At least the way the protocol is written now, I don't think that will work. Because yeah, it won't work because you have like this decryption key that needs to change and stuff. Yeah, sorry,
so
that won't.
It would, but it's still deterministic regardless of the quorum that signs.
Yeah, I mean, this is just a two-party case, but
right.
It'll be deterministic, localized to each epoch.
Okay.
Yes.
just one minor comment on the challenge that you had, the E equals H of RM.
Mhm.
Actually, there's the public key is missing there.
Oh, sure. Yes. That was just, yeah, you're right.
So we have one online question from Tim Roofing. He's essentially asking, one disadvantage of our previous work is that this is restricted to the 2 signers, 2 of 2. Do you see a way to generalize this to more signers?
Yeah, I mean, fundamentally, there's nothing keeping for this work, there's fundamentally nothing keeping the techniques to 2 of 2. But it's just that we work with this like PCF abstraction, and then the previous work for PCFs is only defined for 2 parties. But if you just do some more work to expand the abstraction and reprove all of these like building blocks, then it should work for the n-party setting as well.
Thank you. Next question, please.
Why didn't you look at the like LPN style vols?
Well, I mean, we wanted PCFs rather than PCGs, and the flavor of LPN that you need for PCFs, if I remember correctly, is a bit funky. Like there's this like variable density kind of assumption.
I think there are other ways too.
Oh, okay, I mean, sure, I may not know. There may be works that I'm not aware of, but yeah.
So if there are no more questions, then let's thank the speaker and also the first speaker of the session again. We'll now have a short coffee break and we see us, I think, in roughly 30 minutes, all of you back here. Thank you.